AP Chemistry, this is the answers video to day 4849 rate mechanisms. Signed last Thursday, and it says due Monday, final due Tuesday. Push both of those back. Make the due on Tuesday and the final due on Wednesday. Or I'll take it on Friday if you come to school on Friday. Friday is not a required school day. If you haven't heard that, I just heard it myself. But I'm going to say Wednesday, but it could be Friday as well. And that's going to be November 9th, 10th, 11th, 12th. Okay, there you go. I would get it done as soon as possible because you're going to get a big assignment in this unit over the weekend. You're going to need to know this, okay? Anyway, let's get going on this. Okay, so we're just going to sketch the three main types of zero, first, second order reactions. And so the first one, zero order, is simply the concentration of A. So on the left side, it's going to be concentration of A versus time. And for zero order, that's constant. Remember that the slope, which is this right here, is K. And that doesn't change. You go down here, it's still K. That's the rate of the reaction. That means the rate doesn't change. As concentration goes down, 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 reactants, the concentration goes down of the reactants, but the slope doesn't change, which means the value of K, the rate doesn't change. The rate constant doesn't change, and the rate doesn't change. So the concentration has no effect. No matter whether you have a lot of A or very little of A, the rate is going to stay the same. So linearized is just the same thing. Okay, we're just drawing a duplicate of that line right there. That should look like that line right there, and that's the same line. Okay, now we're going to go on and we're going to do so concentration of A versus T, and it forms a curve that looks like this that you're familiar with. It's steeper at the beginning because the concentration of the reactants is going down much faster at the beginning, and then as you run out of the concentration, this was our little exercise out in the quad where you were bumping into each other, as you have fewer and fewer reactants, it doesn't go down as fast. Okay, so in a unit of time up here, the reaction went down this much right here. In that same unit of time, we'll say right here, trying to make these spaces the same, then you can see it didn't change that much. It didn't go down that much. Okay, so that means the rate of the reaction is slowing down. Now linearized, it's going to be, what you're going to do is plot the natural log of A. And again, the reason we do that is we like to deal with straight lines. And to linearize it, you plot the natural log of a first order reaction. So that slope is K. That tells you what the rate constant is there. And of course it's negative. So that's going to be the how you plot it. So in other words, if you want to know whether a reaction is first order, you simply take the different concentrations, you take the natural log of them like we did, you plot them in a table, and if they form a straight line, which means the differences between them are the same. For example, if I went from 0.9 to 0.7 to 0.5 to 0.3, those all have differences of 0.2. And so that means it's a straight line. The rate of time, 1 second, 2 seconds, 3 seconds, changing in a straight line fashion, and so is the rate of the natural log. Okay, so that's how you would spot that, by plotting natural log against time. If it's a straight line, it's a first order reaction. For a second order reaction, the curve looks very similar to a first order because for the same reasons. At the beginning, the reactants are used up. And then as they get used up, the reaction slows down as you go down there. For that, you're going to plot 1 over the concentration of A against time. And what that will give you, if it is a second order reaction, is it will give you a positively sloping line. So that's K there. That's the slope is K there. All right. So that's how you spot these. So we did that in the last exercise, but you should be able to recognize this, kind of have these memorized. Okay. If I can show them all at the same time, have those memorized. All right. Those relationships. This one is A versus time. It's just identical to this. I'm just copying it a second time. This is natural log versus time will give you a straight line for first order, and 1 over A versus time will give you a positively sloping straight line for second order. All right. Okay, sketch an energy diagram for an exothermic and for an endothermic equation with the explanation of each part of the graph. Identify the activation energy and the total change in energy of the reactant. So very simply, it can look like this. I'm going to draw a bit of a straight line here. And these are going to be reactants A plus B. Let me write the equation. It's going to be A plus B is going to produce C plus D. Okay? And then in order to get these to break apart, you must put energy in. So what it's going to do is it's going to curve up. This is energy up here, and this is time. Okay, so you're plotting the energy in. So energy has to be put in at first. It's going to go up. Then finally it's going to reach a point where A and B are broken apart, whatever they are, and it's going to start to come down. And you're going to end up with products C and D. Okay, so there you have that. All right. So the activation energy, this is the initial energy. We'll call it E sub 0. Get used to that little subscript 0. It means beginning or initial. So that's the E0. And this is going to be the E final, the final energy of the overall reaction system. The activation energy, be careful, it's not this value up here. It's the difference between the energy that the chemical reaction started at and this. So this is the activation energy. And that's EA, activation energy, okay? So let's write that over here. E0 is initial or beginning, if you like the word beginning better. Energy, EF is the final. Okay, that's the activation energy. All right, so it had E0 here and EF here, so it went to a lower energy. That means that energy had to be let off. It had to come out of the reaction for it to go from higher to lower. So delta E, change in energy, is, and we call that enthalpy here, is negative delta H, and that means it's an exothermic reaction. Energy had to come out. Okay, so there it is. So that's exothermic. If we come over here to this one, we're going to draw an endothermic reaction. So it's going to look like this. We're going to start right here. We can start at the same level pretty much. It's going to curve up, and then it's going to come down, and it's going to level off at a higher level of energy than it started at. Okay, so this is EA, and notice it still has pretty much the same activation energy. It's not important that it does or doesn't, but that's going to be the activation energy. And this is going to be E, that should be E0. That was a mistake. That's E0, that's initial energy. This is EA, this is activation energy, and this is E final. Again, we can call this reactants A plus B, reactants C plus D. Okay. Now, this started off at a lower energy and ended up, so it had to take in energy. That's a positive delta H. So the change in energy equals positive delta H, positive enthalpy. And that's an endothermic. Just the word endo sounds like indo. It means energy went into it. Okay? And so you had to have energy go in for it to end up at a higher energy level. Now that might go counter to everything you think you've heard in this class, that things always want to go to lower energy. And once upon a time, chemists thought that all reactions had to be exothermic. They had to go from here to here. But they found out in the real world, hey, there are some that actually take in energy. Those are endothermic. So how does that work if it's taking in energy? The answer to that question will be answered in the last few weeks of this course when we get into a concept called entropy. So there's a different kind of energy. There's another type of energy in effect. It's not really energy, but it's another factor in addition to enthalpy, that when we say something wants to go from higher to lower energy, it's not just enthalpy. It's not just the delta H. It's not just the heat. Remember, this is basically heat. There's another factor involved, and that gives us something called free energy. And we'll talk about that, as I say, later on in the course. So the fact is, you can have endothermic reactions without violating the general principle that chemical systems, physical systems want to go from higher to lower energy. It's just we're talking about a different type of energy that involves enthalpy, but not just enthalpy. And we'll learn about that later. Okay, so let's talk a little bit about these, just a little bit more. What will happen is if you put in enough energy to get up to about here, but not all the way to the top of this hill. It's called the energy hill. It's called that. It'll just fall back, and these will recombine into their original state. You have to get it all the way up over this hill. It's just like rolling a ball up a hill. If you don't push it hard enough, it'll roll back. But if you push it hard enough to get it over the hill, it will roll down to this side. Now, not all reactions go from entirely reactants to products. You're going to learn that when we get into equilibrium in the next unit. But this is essentially, it's called the energy diagram. You should be familiar with it, with what each of these represents. You should be familiar that if it starts off at a higher energy and ends at a lower, that's exothermic. That the activation energy, it's not this energy right here. That's not the activation energy. It's the difference between these two. That's the activation energy. And it's the same over on this one. It's the difference right there between those two. That's the amount of additional energy. Remember that the reactants already have some energy. You have to put in additional energy to get them to break apart. So up here, they're all in a bunch of little individual atoms and particles, and then they get put back together. And when they do that, they release energy. When bonds are formed, they do go to a lower energy state down there. Diagram is something called the Maxwell-Boltzmann distribution. You don't have to know names like this, but it's nice. So if somebody refers to it, you know what they're talking about, but they're not going to test you on the AP exam on names like that. Okay, what it simply does is it says the number of particles on the vertical axis, and on the horizontal is the energy that they have. And somewhere along there, there's going to be the activation energy. That's EA right there, activation energy. So if there's very low energy, the area under the curve represents 100% of the particles, atoms, molecules, whatever they are. So if I draw this very tall, kind of thin curve that looks like this, and it ends right about there, this area represents 100% of the particles. So the most particles would have this energy right here, right at that highest point. That would be what in statistics is called the mode. It's the most common number. So none of the particles have surpassed the activation energy. So this reaction, this would be like AB in here, where all the ABs only have about this much energy, and they can't get over that hill right there. As you increase the temperature and increase the energy, you more and more get a curve that looks like this. It's not quite as tall, but it comes down, and at least some of it goes past the activation energy. So the particles in the shaded region would have enough energy to react, to form a chemical reaction, to break apart and form a chemical reaction. As you give them even more energy, then the curve will be lower but longer, like this. Now all of these represent the same number of particles. So same number of particles in the tall, thin one, same number of particles in the medium one, same number of particles in this one. So they're all 100% of the particles. But now you can see that this one has, the hashed lines that I'm doing here, has that many particles, or percentage, however you want to think of it, that are past the activation energy that can actually react. So number of particles and energy going from left to right, increasing energy as you go to the right. And that's called a Maxwell-Boltzmann distribution. There's never specific numbers attached to this. It's just a conceptual diagram of the energy required to make a reaction take place, okay? And you have to get over the activation energy. Remember, that is this energy right here. You got to get above that. Okay. Now we're going to sketch a graph of the rate constant K versus T temperature. All right, so here's the rate constant on the vertical axis, and here's T on the horizontal axis. Okay, next, sketch a graph of the rate constant versus temperature. So that's out of the video. It looks something like this. Okay, it's not something we'll ever deal with in a numeric problem, because one of the things in all these problems we work in this unit in kinetics, we assume the K stays the same. If K starts changing, that just adds too many complications for this level of chemistry. Okay, so we're not going to assume that. But just to understand conceptually what's happening, that as the temperature gets higher, going from left to right, that the rate constant goes up at a faster and faster rate. So at low temperatures, increasing the temperature, it doesn't go up that much for a given temperature change. But as you get over here for the same amount of temperature change, it starts to go up quite a bit more. Over here for the same one, it goes up quite a bit. Okay, so that's just saying that at higher temperatures, the rate constant will increase faster than at lower temperatures. That's pretty much all you need to know is that concept. There's no numbers that we're going to ever attach to this. Okay. All right. So define the terms unimolecular, bimolecular, and termolecular. So that's straight out of the video, so I'll leave that one for you. Okay. Now we are on to page 3 of the assignment. It says write the Arrhenius equation for the rate constant. Define each variable and which value of R is used for the gas constant. Okay. So here's the equation. Okay, there it is. It's K equals AE raised to this power. So this is all up in the exponent. I wrote it kind of big, and it looks like it's kind of spilling down here. But this is all up in the exponent of E. So it's to the minus activation energy over gas constant times temperature. Temperature must be in Kelvin. Okay, so it's a big mess. Whenever you look at an equation like that, and it just looks like a jumble, here's what you want to get out of it. Is the rate constant is a function of what variables. That's what you want to kind of get out of this. What things contribute to the rate constant in this case, and what things don't. So we've been talking about temperature the whole time, that increase in temperature increases the rate constant, makes the molecules, particles move faster and smash into each other harder and break apart, so the reaction happens faster. So temperature's clearly there. Another thing, though, that we've learned in this last lesson is that activation energy is important. It has to overcome the activation energy or reach that height of the activation energy in order for the reaction to take place. So K is a function also of, is it a high activation energy? If it is, that would make the reaction constant be less, because it would be a lower number because the reaction won't happen as fast. If the activation energy is pretty low, it means the molecules, particles don't have to get up to as high a temperature to react, and therefore K will be higher. The reaction will happen faster. And finally, this one is called the activation factor. And what it simply is, it deals with, it includes a couple of things, but one of them is the orientation of the molecules. They have to hit with a certain orientation in order to break apart. Remember I gave the example of taking the meter stick, and if I bang the end of it against the corner of a table, it won't break. But if I turn it sideways, lengthwise, and smash it against the corner, I can break it very easily. That's where the orientation comes in. And this includes a few things, including orientation. Okay? So orientation, activation energy, and temperature are all included in the rate constant. Remember, the bigger K is, the faster the reaction takes place. Okay, so watch the video. It gives a detailed explanation of what each of these are. If you have questions, then you can come to me and ask me about them. All right, compute the following, similar to a video problem at 1926. So it says the value of constant K is 1.25 times 10 to the -4 seconds at 45 degrees centigrade, 318 K. you have to use K. The activation energy EA is 100,000 joules per mole. It should be per mole Kelvin. No, I take that back. It is mole. Okay, what is the value of the rate constant K at a different temperature? So in other words, what you have is you have K right here, K1, at a certain temperature, T1. And then you know the activation energy, R, we'll talk about here. And then it says, what is the value of K2, question mark, at the different temperature, T2? So you have K1, T2, and T1. You have the activation energy right here. And it is, activation energy right there, and R. Now, R is the gas constant. It's the gas constant just like we use in the ideal gas law, except it's a different number. And the number here is 8.31 joules per mole Kelvin. Okay, the other gas constant that we use in PV equals nRT is 0.0821 liter atmospheres over moles Kelvin. So joules takes the place of liter atmospheres, and therefore the number changes. It's not important to do the derivation of how you got from this to this. It just does. Okay, so there's two different gas constants, and you need to use this one. How do you know which one you need to use? Just experience, just doing every problem that you're assigned to do, and you'll learn over time which one you need to use. Okay, so we're going to go ahead and plug in the numbers, and I'm going to actually let you do this one. You have everything. It's just a plug and chug problem. It just is one that looks kind of complicated. Go ahead and follow the example that's in 1926, and if you want to do it, remember, I'll do any problem with you in tutoring, but it's done exactly the same way as the problem in the video, except we changed the numbers. Okay, so we're going to move on then. Okay, so the last few problems, well, not quite, yeah, the last few problems here are using this Arrhenius equation, and I'll do one of them for you so you see what I'm getting at in doing this, okay? So it says compute the value of K for the following data. So let's go ahead and plug in the numbers. Okay, I'm not going to use all the units of measure because they kind of clutter things up. But anyway, just understand that if you plug these numbers in appropriately, you're going to get the value of K, which would have whatever the proper units of measure for K would be. Remember, that can be different for different types of problems. Okay, so we'll go ahead and solve this one. Okay, so let's go ahead and work on our calculator skills here. First, we're going to take e raised to all of this. So to get to e, you hit second and ln, and right up above the ln, you can't really see it on my screen, but it's e to the x. So there you go, there's e raised to the power. Okay, so what we're going to do is, I like to wrap things in parentheses. You don't really need to here. It already has an open parenthesis. So for the negative 10,000, we're just going to use the negative sign down here. Don't use the minus sign for a negative number. Use that. That's the negative sign for a negative number. So we put a minus 10,000. And then you have two numbers in the denominator. That means you divide by both of them, just like we did in stoichiometry. Divided by 8.31, divided by 300. And don't forget to close the parentheses here. Sometimes that doesn't hurt you, but in this problem, I'm pretty sure it would. So close the parenthesis. There we go. And we get 0.018. And then we multiply what we just calculated is all of this. Now we're going to multiply it by 3, and we get this. Don't worry about units of measure. What I'm trying to accomplish in these problems on this page is to get you to see how K will change with changes in these various variables up here. So we got 0.054, okay? So that's a certain value for K. Now we're going to do this. We're going to change the temperature in the part to 100K. So this is going to go to 100K. So let's go ahead and write that out. And we're going to see how lowering the temperature affects this now. we all pretty much know by now what it's going to do. It's going to reduce K, right? Lower temperature means that K is not as great a number. That means the reaction does not go as fast. But let's see if it happens here in this equation. Part of the reason for doing this, it's a little confusing how changes in this exponent with a negative number in front of it, that might be kind of confusing. How is lowering it from 300 to 100 going to affect K? Is it going to make it go up or go down? It might not be that obvious with this being in the exponent and this being a negative sign in front. So we're going to go ahead and do this. Okay. So again, we're going to take second and ln. That gives us e raised to a power. Close the parenthesis and hit equals and times 3, and it gives us a much smaller number, right? I should write this in scientific notation, but let's just go ahead and write it out in standard decimal form so you see that it is much smaller. And I'm going to just cut it off there at 0.18. So that's a much bigger number than that. So lowering the temperature by 3 times, in other words, I mean, this is much less than 3 times this. So you can see that lowering the temperature by 3 times, this became many times lower than this. Okay, so that's what I wanted you to see here. So answer the question, what happened to the rate constant and why? So the rate constant, let's answer this question together. Because temperature was lowered, okay? And I think you know what the consequence of that is. The molecules don't move as fast, they don't hit each other as frequently or as hard, and therefore the reaction slows down and the rate constant is going to be reduced. Okay, let's do C together. Why not? And then I'll leave D for you to do, but remember to do it and explain it. So it's just plugging in the numbers. Now we're going to increase the frequency factor. We're going to double it from 3 to 6. And I think you can see what's going to happen to the rate constant. So now we're going back to the original data. So put the temperature back at 300. Don't keep it at 100. We want everything to be the same except this is what we're going to change. And I think most of you can look at that and see what's going to happen. So let's go ahead and do it though. So this is the number we changed. And now we're putting the temperature back to 300 K. Again, start with the E first. Okay, and so it became, something didn't go right there. Let me try it. Oh, I didn't multiply by 6. Let me try it again. Okay, always time to do it over. Okay. Divided by these two. Close parenthesis equal. And now I have to multiply it by the 6. Okay, and if you don't recognize it, since we doubled this number from 3 to 6, we doubled this number too. So that's what we get here is we get 0.109. I'll just leave it there, 0.109. So this number is twice this number because we doubled the frequency factor. So that means whatever that includes, it's kind of vague what that includes. You don't have to really understand. It is orientation. It's one of the things. That's going to go ahead and make the reaction go faster. So K went up. This number for K is greater than this number. All right, so what happened and why? Okay, all right. And then the last thing you're going to do is go back to the original data, this data set right here, except you're going to change one thing. You're going to change the activation energy from 10,000 down to 5,000. So what's that going to do? If you reduce the activation energy, is that going to make the reaction go faster or slower? Well, plug in the number. Keep all the other numbers the same as they are up here. So that number right there, that EA, is going to become 5,000 down here. And then see if K is greater than or less than 0.054 from your original. Okay, so I'll leave that one for you to do. Come see me if you want some help on that. Okay, finally, glow sticks. I think we'll talk about this one in class, so I'm going to leave this one. But I want you to think about these. Again, this could be this is the type of question AP likes to ask. in the sense that it's a descriptive, it's why did something happen. They like to ask why did this happen, not just crunch numbers and give them a final number. They want to know why did something happen. Explain what was going on. So explain why the brightness of the glow sticks changes as they're placed in different beakers of water, meaning different temperature waters, right? In the rate equation, so there's the general rate equation. What part of the equation is affected by placing the sticks in beakers at different temperatures? Which one of those variables is changed? And C, is it possible that the concentrations of the reactants A and B could have an effect on the brightness? Okay, pretty straightforward questions. So ask those and we'll talk about those in class. That takes care of this answers video, and we'll see you in class.